In this lecture, I will answer two questions. In the first question, we find out the radius of this circle that blocks coordinate ABCD. And in the second question, we find out the length of line segment AP that equals to x. We have to find out the value of x. So we'll start with the first question. In the drawing, we have quadrilateral ABCD that is inscribed by this circle. Note that AB equals to BC. AC is the diameter of this circle. The perimeter of this quadrilateral ABCD equals to 18 units. That is to say, the sum of its side lengths in total is equal to 18. AB plus BC plus CD plus DA equals to 18. And we know that the area of this quadrilateral ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle that blocks quadrilateral ABCD. So first of all, we will define the side lengths of quadrilateral ABCD with letters. We define the length of side AB as A. Side AB equals to side BC in its length, therefore BC must be also equal to A units in its length. Likewise we define the length of side AD of quadrilateral ABCD as B, and we define the length of side DC as C. So here we can implement rule 7. I'll quickly rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of the circle, and therefore peripheral angle ACB is equal to 90 degrees in its size. So according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. One put in our drawing. We have peripheral angle ABC that subtends on chord AC, that is the diameter of the circle, and therefore peripheral angle ABC must be equal to 90 degrees in its size according to rule 7. Likewise, this is peripheral angle ADC that subtends on the same chord called AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size according to rule 7. In the next step, we will implement the Pythagoras theorem on both those right angles, on this right angle ABC and on this right angle ADC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is the relation for Pythagoras theorem. This right angle ABC, according to Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, according to the Pythagoras theorem, this right angle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so with the cities, it is AC square equals to AB square. AB is A, therefore AB square is A square plus BC square. BC is also A, so BC square is A square. So in total, if we found out that AC square equals to A square plus A square, that is 2A square. AC square equals to 2A square. According to equation 1. The next step, we implement the Pythagoras theorem in the right triangle ADC. So in this right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, is equal to AD square plus DC square. And again, this right line ADC, according to the Pythagoras theorem. So Pythagoras theorem, AC square equals to AD square plus DC square. AC is the missing side, so it is AC square equals to AD square. AD is B, therefore AD square is B square plus DC square. DC is C, therefore DC square is C square. So in total, according to equation 2, if we found out that AC square equals to B square plus C square. This is according to equation 2, and according to equation 1, we already found out that AC square equals to 2A square. So we have two different equations for AC square. Therefore, we get equation 3 that says that AC square according to equation 1 must be equal to AC square according to equation 2. So question 3 states that AC square according to equation 1 must be equal to AC square according to equation 2. AC square according to equation 1 equals to 2A square, and it must be equal to AC square according to equation 2 is equals to B square plus C square. So in total, according to equation 3, we found out that 2A square equals to B square plus C square. Here we divide this equation 3 by 2, and finally we get that according to equation 3, A square equals to B square plus C square over 2. The parameter of this quadrilateral ABCD equals to 18. That is to say A plus B plus C equals to 18. A plus A is 2A plus B plus C equals to 18. So 2A plus B plus C equals to 18. This is equation 4. It is given as the equation that the area of this quadrilateral ABCD equals to 16 square units in size. Quadrilateral ABCD consists of two shapes. The first shape is this right triangle ABC. This is the second shape, that is actually right triangle ADC. Therefore, the area of quadrilateral ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of this first shape, that is the area of this right triangle ABC, plus the area of the second shape that it consists of, that is the area of this right triangle ADC. So in total, the area of the big quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape that it consists of, that is actually the area of the right triangle ABC, plus the area of the second shape that it consists of, that is actually the area of the right triangle ADC. This gives us the equation that the area of quadrilateral ABCD equals to 16 square units in its side, so we substitute the area of quadrilateral ABCD by 16. This equals to the area of triangle ABC plus the area of the right triangle ADC. What is the area of this right triangle ADC? The area of this right triangle ABC equals to the base AB times the height BC over 2. AB is A, BC is also A, divided by 2. So it is A times A over 2, or A times A is A squared over 2. So the area of the first shape, that is the area of the right triangle ABC, equals to A squared over 2 square units in its sides, plus the area of the second shape, that is on the other ABCD consists of, is actually the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD times the height DC over 2. AD is B, DC is C, so in total it is B times C over 2. The area of the second shape in total equals to B times C over 2 square units in its size. So in total we found out that according to equation 5, 16 equals to A square over 2 plus BC over 2 square units in its size. Here we multiply this equation 5 by 2, and finally we get that 16 times 2 is 32 equals to A square over 2 times 2 is A squared plus BC over 2 times 2 is BC. So in total we found out that according to equation 5, 32 equals to A squared plus BC. And again, according to equation 5, we found out that 32 equals to A squared plus BC. According to equation 3, A squared equals to B squared plus C squared over 2. And therefore, we can substitute A squared in this equation 5 by B squared plus C squared over 2 from equation 3. We do it now, and it's that according to equation 5, 32 equals to A squared, and A squared according to equation 3 is B squared plus C squared over 2, and also plus BC. So in total, according to equation 5, we found out that 32 equals to B squared plus C squared over 2 plus BC. Here we multiply BC by 2 and then we divide it by 2 in order to become comfortable with this expression. So we get that according to equation 5, 32 equals to B squared plus C squared over 2. And we have to multiply BC by 2 and then we divide it by 2. So 2 times BC divided by 2. So in total we found out that according to equation 5, 32 equals to B squared plus C squared plus 2 times B times C over 2. Here we multiply this equation 5 by 2. And finally get that according to equation 5, 32 times 2 is 64 equals to B squared plus C squared plus 2 times B times C. And again, according to equation 5, and we found out that 64 equals to B squared plus C squared plus 2 times B times C. So here we use the algebraic identity that says that a squared plus b squared plus 2 times a times b equals to a plus b squared. According to this algebraic identity, we get that b squared plus c squared plus 2 times b times c equals to b plus c squared is equals to 64. So total, according to equation 5, we shall find out that b plus c squared equals to 64. Here we will take out all of this equation, and finally get that according to equation 5, b plus c equals to 8. b plus c equals to 8. But according to equation 4, we only found out that 2a plus b plus c equals to 18. Because of the fact that according to equation 5, b plus c equals to 8, we can substitute b plus c in this equation 4 by 8. We do it now, and get that according to equation 4, 2a plus b plus c, and b plus c is 8 according to equation 5. So 2a plus 8 equals to 18. Here we subtract 8 from this equation 4, and finally get that according to equation 4, 2a equals to 18 on 8 is 10. So 2a equals to 10. Here we divide this equation 4 by 2, and finally get that a equals to 10 over 2 is 5. So according to equation 4, a equals to 5 units in its length. AB equals to a equals to 5. Likewise, we see that also equals to a equals to 5. So in total, we found out that AB equals to BC equals to 5. So in the next step, we implement the Pythagoras theorem on this right triangle, triangle ABC. Going to the Pythagoras theorem, this right triangle ABC, AC squared, the square of the hypotenuse, equals to AB squared plus BC squared. And again, according to the Pythagoras theorem, in this triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25. Plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total, we shall find out that AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we substitute 50 by 20 times 2. And we get that AC squared equals to 25 times 2. So here we take out all of this equation, and finally we get that AC, the bonus AC equals to the square of 25, that is 5. So inside the root we have to leave with 2. So AC equals to 5 times root of 2, and it's in its length. AC is the hypotenuse of those two right triangles, but AC is also the diameter of the circle. And find the radius of this circle is R. And find the radius of this circle is R. The radius of the circle is equal to the diameter over 2. So the radius that we are looking for, radius of the circle, is equal to the diameter AC over 2. AC is 5 times root of 2. If we divide it by 2, we get the radius. So total the radius of geometry for this question, the radius of the circle equals to either 5 times square 2 or 5 times square root of 2 over 2 units in its length. On terms of numbers, it is equals to 3.536 units in its length. And again, the radius of this circle, that is the radius that you are looking for this question, it is equal to either 5 times square root of 2 over 2 units in its length. In terms of numbers, it is equal to 5.3536 units in its length. Again, the radius of the circle equals to either 5 times square root of 2 over 2 units in its length. In terms of numbers, it is equal to 3.536 units in its length. So we finished the answer on the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. The second question, our task is to find out the length of this line segment AP. That is equals to x. We have to find out the value of x. In the drawing, we have a circle that is described by this right angle ABC. QS equals to 25, chord QP equals to 24, ABC is the right angle. This is the tangent to the circle at this point. We define the point of tendency of this tangent with this circle. This point is point M. So SM is the tangent of the circle, point M. So again, our task is to find out the length of this line segment AP that equals to x. We have to find out the value of x. So first of all, we will implement rule 2 in our drawing. Okay, quickly on rule 2. According to rule 2, the lengths of two tangents from a common point to a circle are equal. In the drawing, we have a circle. This is the common point, point P. From this common point, point P, we have two tangents to this circle. Tangent PA and tangent PB. According to this rule, all two are equal to each other. That is to say, PA equals to PB. Or the length of tangent PA equals to the length of tangent PB. PA equals to PB. So we can implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common point, point A, from this common point, point A, we have two tangents to this circle. Tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ, but AP equals to x, therefore AQ must be also equal to x units in its length. In the next step, we will define the length of this short tangent BM as A. And we will focus on this common point, point B. From this common point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to A, therefore BQ must be also equal to A units in its length. In the next step, we focus on this common point S. For this common point S, we have tangent PM to the circle, that is tangent to the circle at point M. This is chord PQ, the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. Okay, quickly on rule 10. Rule 10 is true in any circle, so in any circle, if AB is any chord in the circle, and PT is a tangent to the circle, Then the following equation is true, that Pt square equals to Pa times Pb, again Pt square equals to Pa times Pb. So in the drawing we have a circle, this is the common standpoint point P. For this common standpoint point P we have tangent Pt, that is tangent to the circle point T. And we also have, this is called VA, the extended called VA touches point P. So in this line, the following equation is true, that Pt square equals to Pa times Pb, again Pt square equals to Pa times Pb. So as I said before, we can implement rule 10 on the common standpoint point S, while for the common standpoint point S we have tangent Sm, that is tangent to this circle point M. Likewise, the extended called PQ touches point S. Therefore, all the requirements of rule 10 are satisfied, and therefore we can implement in rule 10. So at the dawn, if we focus on the common standpoint point S, according to rule 10, the following equation is true, that Sm square equals to Sq times Sp. Again, Sm square equals to Sq times Sp. Again, if we focus on the common standpoint point S, the following equation is true, that Sm square equals to Sq times Sp. Sm is the missing tangent, so we leave it as it is, so it is Sm square equals to Sq is 25 times Sp. Sp in total equals to Sq, that is 25, plus Qp, that is 24. So in total Sp equals to 25 plus 24, that is 49. Okay, again, if you found out that Sm square equals to Sq times Sp. Sm is the missing side, so it is, so it is Sm square equals to Sq times Sp. Sq is 25 times Sp is 49. So in total, if you found out that Sm square equals to 25 times 49. Here we take out all of this equation, and find again that Sm, the missing tangent Sm equals to the square root of 25, that is 5, times the square root of 29, that is 7. So in total, Sm equals to 5 times 7. 5 times 7 is 35. So in total, we shall find out that the length of tangent Sm is equal to 35 units in its length. This is tangent Sm, is equals to 45 units in its length. What is the length of this missing line segment? Line segment SB. SB in total equals to Sm minus Bm. Yeah. SB equals to Sm minus Bm. So writing on. The missing line segment SB equals to Sm minus Bm. So SB in total equals to Sm, that is 35, minus Bm, that is 8. So in total, SB equals to 35 minus units in its length. Sm is a tangent to the circle at point M. So Sm is a tangent, Sm is a tangent. It is absolutely straight line. So if you focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line SM at point B? We have this angle, it is a right angle, plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. And therefore, triangle QBS is a right triangle. In the next step, we'll implement the Pythagoras theorem on this right green triangle, triangle QBS. Here by P it is a version for Pythagoras theorem. According to the Pythagoras theorem, in this right green triangle QBS, QS squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. And again, according to the Pythagoras theorem, and this green right triangle QBS, QS squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. QS is 25, therefore Q squared is 25 squared, it is 625. And it is equals to QB squared. QB is 8, therefore QB squared is 8 squared. Plus BS squared. BS is 35 minus 8, therefore BS squared is 35 minus 8 squared. So in total, we should found out that $625 equals to a squared plus 35 minus a squared. So 625 equals to a squared plus 35 minus a squared. 35 minus a squared equals to 35 squared, that is 1225 plus a squared must 2 times 35 times 8, that is 178. So 625 equals to a squared plus a squared is 2a squared, and we have here 178 plus 1225. So in total, if you found out that 625 equals to 2a squared, 178 plus 1225. Here we subtract 625 from this equation. So in this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 2a squared, 178, and 1225 minus 625 is 600. So in total we should find out that 2a squared minus 78 plus 600 equals to 0. So here we divide this equation by 2. And finally, we get that 2a squared over 2 is a squared, 178 over 2 is 145a, 600 over 2 is 300, and 0 over 2 is 0. So in total, we found out that A square minus 45A plus 300 equals to 0. So actually this is a quadratic equation. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula for quadratic equation, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. A, B, and C are of course the coefficients of this general quadratic equation. In our specific quadratic equation, that is to say a squared minus 45a plus 300 equals to 0, the variable that we are looking for is a. Therefore, x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 45. And finally, the coefficient c equals to 300. So, we have all the data that is needed in order to find out the value that we are looking for this our specific quadratic equation, that is a. The only thing that is left to do is to put the data that we have for our specific quadratic equation inside this general formula for x. In this way, we get the value of the values of a, because x equals to a. We have to find out the value that we are looking for in our specific quadratic equation is a. So x equals to a, so we substitute x by a. And it is equals to minus b. b is minus 45, therefore minus b is minus 45, that is plus 45. Plus minus square root of b squared. b is minus 45, therefore b squared is minus 45 squared, that is 1225. Minus 4 times a times c. A is 1, c is 300, so minus 4 times a times c is minus 4 times 1 times 300, that is minus 1200. Over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, if you found out that a, that is the variable that we are looking for, quadratic equation, specific quadratic equation, a equals to 35 plus minus. Inside the root we have 1225 minus 1200, that is 25 over 2. In total, if you found out that a, that is the variable that we are looking for, equals to 35 plus minus, the square root of 25 is 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20, while the second solution for a is a equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for a is that a equals to 15. So we have two solutions that are possible for a. The first solution for a is 20, the second solution for a is 15. What is a? A is the length of this 900 QB, and a is also the length of tangent BM. So why a is so important to us? Our task is to find out the length of line segment AEP that equals to x. we find out immediately why A is so important to us. We have to find out the value of A. So, in the next step, we'll do the construction, but before that, this is triangle APQ. The red triangle APQ is an associated triangle because side AQ equals to side AP. QP is of course the best of this associated grand triangle, triangle AQP. And QP is the best of the associated triangle, triangle AQP. So in the next step, we will do a construction, that is to say from the vertex A, we will do perpendicular to the base QP. Again, from the vertex A of the associated triangle, AQP, we will do perpendicular to the base QP. Actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in the base QP. This point is point Z. So, here the associated grand triangle AQP, and we do perpendicular AZ to the base QP. So here, you can implement here rule 21 on the associated grand triangle, triangle AQP. Repeat quickly on rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. And the drawing, we have the associated triangle, triangle ABC. Side AB equals to side AC, and therefore triangle ABC is an associated triangle. BC is of course the base of this associated triangle, triangle ABC. From the vertex A, we do perpendicular AO to the base BC. Again, from the vertex A, we do perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this rule 21, the perpendicular AO to the base BC bisects the base BC. If AO bisects BC, it means that it divides side BC into two halves. Each half, of course, must be equal to BC over 2 because BC has been bisected by AO. So the first half, BO, of course, must be equal to the second half OC, and each half must be equal to BC over 2. So BO equals to OC equals to BC over 2. Okay, so we can implement rule 21 in our drawing. In our drawing, we have the perpendicular AZ to the base QP. According to rule 21, the perpendicular AZ to the base QP bisects the base QP. So the first half is QZ, and it is of course equal to the second half ZP. And each half must be equal to ZP over 2, because ZP has been bisected, because QP has been bisected. So QZ equals to ZP equals to QP over 2, according to rule 21. So the associated triangle, triangle AQP, according to rule 21, QZ equals to ZP equals to QP over 2. Again, in the isosceles green triangle in QP according to rule 21. The first half of QP is QZ, and it is of course must be equal to the second half of QP, that is ZP, and each half must be equal to QP over 2 because QP has been bisected by the perpendicular. QP is 24, therefore QP over 2 is 24 over 2, that is 12. From this equation, we know that QZ equals to ZP equals to 12. QZ equals to ZP equals to 12. This is the answer QZ. That is equals to 12 units in its length. Likewise, this is the answer ZP. That is also equals to 12 units in its length according to rule 21. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angle as alpha, then the size of this vertex angle must be also equal to alpha because they are equal to each other. So in this wide green triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the small right green triangle QSB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that the small green triangle QBS is similar to the big right triangle AQZ according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So I shall find out that all the figures of this right small green triangle SQB are correspondingly equal to all the figures of this big right triangle AQZ, and therefore those two right green triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that this is the green small triangle QSB, the green small right triangle QBS. That it is similar to this big right triangle AQZ. According to angle similarity rule. And again, we should find out that the small green triangle QBS is similar, this is the sign of similar, to to the big green right triangle AQZ according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side QS of this small green triangle QBS or side AQ of this big right triangle AQZ equals to side QB of this small green triangle SQB or side QZ of this green right big triangle AQZ. This again for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side QZ of the small green triangle QBS or side AQ of the big right triangle AQZ is equal to side QB of the small green triangle QBS or side QZ of the big right triangle AQZ. QS is 25 over AQ. AQ is X, that is the variable that we are looking for in this question. And it is equal to QB. QB is A or QZ. QZ is 12. So in total, if we found out that 25 over X equals to A over 12. Here we will first multiply this equation. If I get that 25 times 12 is 300 equals to 8 times X. Or 8 times X equals to 300. Here we divide this equation by A and finally get that X, that is the variable that we are looking for, is equal to 300 over A. X equals to 300 over A. So now it is very clear why A is so important to us. Because if A equals to 20, then X equals to 300 over 20, that is 15. And if A equals to 15, then X equals to 300 over 15, that is 20. Then X equals to 20. Okay. So you have to find out what is the real value of A. Maybe A could be equal to 20 and 15 because we have two solutions for A. Maybe we have only one solution for A. A could be equal to either 15 or 20. So in order to find out what is the real value of A, and copy this right triangle ABC with the circle that is inscribed inside it, the new drawing, and analyze the new drawing in order to find out what is the real value of A. So actually, this is the right triangle ABC, with the coordinate for the original drawing with the circle that is inscribed inside it. We already found out that QB equals to A, AQ equals to X. So analyze this drawing in order to find out what is the real value of A. First of all, we define the point of tendency of tangent BC with this circle. This point is point M. Likewise, we define the center of this circle. This point is point O. We define the radius of this circle as R. And then we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle that equals to R according to our definition. The radius OM that equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. This is point Q, that is the point of tendency of tangent AB with this circle. So in the next step, we join points O and Q together by straight line. OQ is of course the radius of this circle, that equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the small quadrant Q, O, and B, we have 1, 2, 3 angles, and therefore this fourth piece angle must be equal to 90 degrees in size, according to the rule that says that the sum of the angles in any quadrant is equal to 360 degrees. So inside the quadrant Q, O, and B, we have 4 right angles, and therefore it is a left angle according to rule 5. But we also know that the opposite sides of rectangle are equal to each other. So in the small rectangle Q, O, and B, side OM must be equal to the opposite side QB. But OM is out, therefore the opposite side QB must be also equal to R units in its length. So actually QB equals to A and QB also equals to R. In the next step, we will do a construction, that is to say, we will extend the radius MO. That equals to R, we will extend the radius MO by a straight line until it touches the circle. And we define the touching point of the extended radius MO with this circle. This point is point Z. We extended the radius MO. This is a straight line by straight line. When you extend a straight line by straight line, the result MZ must be also a straight line. So MZ is a straight line. If we focus on the right side of the straight line ZM at point O, here the sum of the areas must be equal to 180 degrees according to rule 3, that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of ZM at point O? We have this angle that is the right angle plus this BC angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this BC angle must be equal to 90 degrees and inside according to rule 3. In the next step, we will do another construction, that is to say from AB, from side AB of this triangle ABC, we will go tangent to the circle at point Z. Again, from AB, we go tangent to the circle at point Z. It is definitely possible because we can find out the right point, that from that right point, we go tangent to the circle at point Z. And we define the touching point of this tangent to, with the side AB, this point is point T. Repeat again, that TZ is a tangent to the circle as point Z according to our construction. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of this circle, is equals to R. The radius OZ is equals to R, the radius OZ is drawn to point Z, that is the point of tangent of tangent Z with this circle. And whenever you have a radius that is drawn to the point of tangent Z, then tangent Z will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to Rule 1. So in total, in the upper quadrangle, TZ or Q we have 1, 2, 3 rectangles, and therefore this 4 pieces must be equal to 90 degrees in size, according to Rule 5. So in quadrangle TZ or Q we have 4 rectangles, and therefore it is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in the upper rectangle TZ or Q, side ZO must be equal to the opposite side TQ, but ZO is R, this is the radius of the circle, therefore TQ must be also equal to R units in its length. We already found out that QB equals to A and QB also equals to R. So write it down. We already found out that QB equals to A and QB also equals to R. What about line segment AQ? AQ equals to X, but AQ consists of two line segments, AT plus TQ. So AQ in total equals to AT plus TQ. TQ is R, so in total AQ equals to AT plus R. So AQ equals to X and AQ also equals to AT plus R. So I write it down. So AQ equals to X and AQ also equals to AT plus R. AT is the length of this line segment. AT is a length, it is absolutely a positive number. AT plus R, it is definitely greater than R because AT is a positive number. So you can write here that AT plus R is greater than R. And from this long inequality, we will derive that A is smaller than X. A is smaller than X, so X is greater than A. Okay, X is greater than A. X is greater than A. So we just right now found out that X is greater than A, and we have two solutions that are possible for A. A could be equal to either 20 or A could be also equal to 15. We only found out that X equals to 300 over A. We can argue that X equals to 300 over A. So if a equals to 15, it means that x must be equal to 300 over 15, that is 20. And again, if a equals to 15, then x must be equal to 20. Likewise, if a equals to 20, then according to this equation, x must be equal to 300 over 20, that is 15. And again, if a equals to 20, then according to this equation, x must be equal to 15. So x equals to 15, and 15 is definitely less than 20, and 20 equals to a, so 20 equals to a, and from this inequality, x equals to 15, it is less than 20, it equals to a, we derive that x is less than a. X is less than a. It contradicts our previous findings that x must be greater than a. If x must be greater than a, x cannot be less than a. So due to this contradiction, we tested the solution that a equals to 20, a can never be equal to 20. So we take into account only the second solution for a, that a equals to 15. If a equals to 15, then x equals to 20. And 20 is definitely greater than 15, and 15 equals to a. 15 equals to a. From this inequality, we derive that x is greater than a. X is greater than a. And exactly like we already found out that x was greater than a. So the final answer to this question is that x equals to 20, AP that equals to, again AP is equals to x is equals to 20 units in its length. Okay, again, if you found out that 9/7 AP is equals to x is equal to 20 units in its length. So in the next step of our lecture, we'll start with the first question, repeat on the solution of the first question, and then repeat on the solution of this second question. first question, our test was to find out the radius of this circle that blocks quadrangle ABCD. So, in the drawing, we have quadrangle ABCD that is described by this circle. We know that AB equals to BC. We also know that AC is the diameter of this circle. You know that the perimeter of this quadrangle ABCD equals to 18. That is to say, the sum of its side lengths in total equals to 18. AB plus BC plus CD plus DA equals to 18. In addition, we know that the area of this quadrangle ABCD equals to 16 square inches in its size. Again, our test is to find out the area of this circle that blocks quadrangle ABCD. So first of all, we define the side lengths of this quadrangle ABCD with letters. We define the length of side AB as A. AB equals to BC, therefore BC must be also equal to A. We define the length of AD as B, and we define the length of this side CD as C. The next step, we implemented all 7 in our drawing. Let's click on all 7. According to all 7, if a peripheral subset of the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is the peripheral CD. The subset of chord AB, that is the diameter of this circle, and therefore it is equal to 90 degrees in its size. So according to this rule 7, any peripheral angle, the subset of the diameter of the circle, must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. In our drawing, we have the peripheral angle ABC, the subset of chord AC, that is the diameter of this circle, and therefore according to rule 7, it must be equal to 90 degrees in its size. Likewise, this is peripheral angle ADC, that also subset on the same chord called AC, that is the diameter of this circle, and therefore according to rule 7, is equal to 90 degrees in its size. Okay. So in the next step, we implemented the theorem on those both those two right angles. This is the right angle ABC, and on this right angle ADC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right angle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, must be equal to AB squared plus BC squared. And again, according to the Pythagoras theorem, this right angle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so there it is. It is equals to AB squared plus BC squared. AB is A, BC is also A. Therefore, AB squared is A squared, and BC squared is also A squared. So in total, if you found out that AC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared, according to this equation, equation 1. In the next step, we implemented the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, and this right triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. And again, the right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. AC is the missing side, so we leave it as it is, and it is equals to AD square. AD is B, therefore AD square is B square. Plus CD square. CD is C, therefore CD square is C square. So in total, if you found out that AC square equals to B square plus C square. And again, in total, if you found out that AC square equals to B square plus C square, according to equation 2. So we have two different equations for AC square. According to equation 1, AC square equals to 2A square, while according to equation 2, AC square equals to B square plus C square. Therefore, we created equation 3 that says that AC square according to equation 1 must be equal to AC square according to equation 2. And again, so the equation 3 that says that AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared and must be equal to AC squared according to equation 2. AC squared according to equation 2 equals to B squared plus C squared. So in total, according to equation 3, we found out that 2A squared equals to B squared plus C squared. Here we divided this equation 3 by 2, and we found out that according to equation 3, A squared equals to B squared plus C squared over 2. We give us the equation that the perimeter of this quadrilateral ABCD equals to 18 units. That is to say, AB plus BC plus CD plus DA equals to 18. Or A plus C plus B equals to 18. A plus A is 2A plus C plus B equals to 18. So 2A plus B plus C equals to 18. 2A plus B plus C equals to 18. It was also given us the equation that the area of this quadrilateral ABCD equals to 16 square units in size. So, quadrilateral ABCD consists of those two shapes. That is to say, this is the first shape, that is the rectangle ABC, and this is the second shape, that is the rectangle ABC. Therefore, the area of the quadrilateral ABCD in total must be equal to the sum of the areas of those two shapes that it consists of. So in total, the area of quadrilateral ABCD must be equal to the area of the first shape that it consists of, that is actually the area of the rectangle ABC, plus the area of the second shape that it consists of, that is the area of the rectangle ABC. The area of quadrilateral ABCD is 16, so we substitute the area of quadrilateral ABC by 16, and it equals to the area of the rectangle ABC. The area of this rectangle ABC equals to the base AB times the height BC over 2. AB is A, BC is also A, divided by 2. So it is A times A over 2. A times A over 2 is A squared over 2. So I'm sure found out that the area of the rectangle ABC equals to A squared over 2 square units in size. Plus the area of this right triangle ADC. The area of this right triangle ADC equals to the base DC times the DA over 2. DC is C, DA is B over 2. So it is C times B over 2. So in total, the area of this right triangle ADC equals to C times B over 2. Or B times C over 2. So in total, the area of the second shape is equals to B times C over 2. So in total, we found out that 16 equals to A squared over 2 plus BC over 2. Here we multiply this equation 5 by 2, and we found out that 16 times 2 is 32, and it is equals to A squared over 2 times 2, that is A squared, plus BC over 2 times 2, that is BC. So in total, according to equation 5, we actually found out that 32 equals to A squared plus BC. This is according to equation 5. And again, according to equation 5, we found out that 32 equals to A squared plus BC. And according to equation 3, we already found out that A squared equals to B squared plus C squared over 2. Now we can substitute A squared in this equation 5 by B squared plus C squared over 2 from equation 3. We did it, and we found out that 32 equals to A squared, that is B squared plus C squared over 2 plus BC. So in total, according to equation 5, we found out that 32 equals to B squared plus C squared over 2 plus BC. Here we multiplied BC by 2 and then we divided by 2 in order to overcome part of this expression. So in total, we found out that 32 equals to B squared plus C squared over 2, and we multiplied BC by 2 and then we divided by 2. So it is 2 times BC over 2. So in total, we found out that according to equation 5, 32 equals to B squared plus C squared plus 2 times B times C over 2. So here we multiply this equation 5 by 2, and we found out that 32 times 2 is 64 equals to B squared plus C squared plus 2 times B times C. Again, 64 equals to B squared plus C squared plus 2 times B times C. Here we use the algebraic identity that says that A squared plus B squared plus 2 times A times B equals to A plus B squared. according to this algebraic identity, we get that b squared plus c squared plus 2 times b times c equals to b plus c squared, and it is equal to 64 according to equation 5. According to equation 5. So total according to equation 5, we found out that b plus c squared equals to 64. So here we took out all of this equation and found out that the square root of b plus c squared is b plus c, and the square root of 64 is 8. So in total, according to equation 5, we found out that b plus c equals to 8. This is according to equation 5. And according to equation 4, we only found out that 2 times a plus b plus c equals to 18. Because we found that b plus c equals to 8, we can substitute b plus c in this equation 4 by 8. We did it when we found out that 2a plus b plus c, that is 8, equals to 18. Here we substitute 8 for this equation 4, and we found out that 2 equals to 18 minus 8 is 10, so 2 equals to 10. Here we divided this equation 4 by 10, and we found out that a equals to 10 over 2, that is 5. And again, we should found out that according to equation 4, a equals to 5 units in its length. So this is side AB equals to 5 and A equals to 5, therefore AB equals to 5. This is side BC equals to A and A equals to 5, and therefore BC equals to 5. So AB equals to BC equals to 5. So in the next step, we implemented the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So again, in the right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so leave it as it is, and is equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. AC is also 5, so BC squared is 5 squared, that is 25. So in total, if you found out that AC squared equals to 25 plus 25, that is 50. Here we substitute, so AC squared equals to 50. Here we substitute 50 by 25 times 2, so in total, AC squared equals to 25 times 2. Here we took out of this equation and found out that AC equals to the square root of 25 is 5, so inside the root we left only with 2. So in total, we found out that AC equals to 5 times square root of 2 units in its length. AC is the diameter of this circle, that is equals to 5 times square root of 2 units in its length. The radius R, that is the radius that we are looking for, must be equal to half of the diameter. That is to say, it must be equal to AC over 2. The radius R must be equal to the diameter AC over 2. That is to say, it must be equal to 5 times square root of 2 over 2. 5 times square root of 2 over 2. So the radius that we are looking for this equation, that is the radius of this circle, equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, it is equal to 3.536 units in its length. So we finished to repeat on the first question. In the next step, I'll repeat on the solution of the second question of this lecture. Our task in the second question is to find out the length of this line segment AP, that is equals to x. We have to find out the value of x. So in the drawing, we have a circle that is described by this right triangle ABC. Again, ABC equals to 90 degrees. We know that QS is 25, chord QP equals to 24. This is a tangent of the circle at this point, so we find the point of tendency of this tangent with this circle is point M. So SM is a tangent of the circle at point M. Again, our task is to find out the length of this line segment AP is equals to X. So we have to find out the value of X. So first of all, we implemented rule 2 in our drawing. So take quickly on rule 2. According to rule 2, the lengths of two tangents from common point to a circle are equal. So in the drawing, we have a circle. This is the common point P. From this common point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, all two are equal to each other. This is to say the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, we have, this is the common point A. From this common point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. This is to say AP equals to AQ, but AP equals to X, therefore AQ must be also equal to X units in its length. We find the length of this tangent, short tangent BM as A. And we focus on this common point B. From this common point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. This is to say BM equals to BQ, but BM equals to A, therefore BQ must be also equal to units in its length. In the next step, we focused on this common point S. From this common point S, we have tangent SM, that is tangent to this area is point M. Likewise, this is chord QP, the extended chord QP touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. Let's click on rule 10. Rule 10 is true in any circle, so in any circle, if AB is any chord in the circle, and PT is the tangent to the circle, then the following equation is true, that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So in the drawing, we have a circle. This is the common point P. From this common point P, we have tangent PT, that is tangent to the circle is point T. Likewise, this is chord BA, the extended chord BA touches point P. So in this drawing, the following equation is true. PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So as I mentioned before, we can implement rule 10 and this common point S. Why? Because from the common point S, we have tangent SM, that is tangent to this circle is point M. Likewise, this is chord PQ, the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true, that SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. Again, according to rule 10, if we focus on the common point S, the following equation is true, that SM squared equals to SQ times SP. SM is the missing tangent, so here it is. And it is equal to SQ, that is 25, times SP. SP in total equals to SQ, that is 25, plus QP, that is 24. So in total, SP equals to 25 plus 24, that is 49. So SM square equals to SQ times SP. So SM square equals to SQ, that is 25, times SP, that is 49. So in total, if you follow that according to rule 10, SM square equals to 25 plus 25 times 49. Here we took out all of this equation and found out that SM, the intended SM equals to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, SM equals to 5 times 7, that is 35. SM equals to 35. This is the misintended SM. This equals to 35 units in itself. What is the length of this missing line segment SB? SB equals to SM minus BM. SB equals to SM minus BM. So SB in total equals to SM, that is 35, minus BM, that is 8. So in total, SB equals to 35 times units in itself. SM is a tangent to the second point. Then therefore, SM is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line SM at point B, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of SM at point B? We have this angle that is right angle plus this missing angle, and total the sum of those two angles must be equal to 180 degrees. 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, therefore, the green triangle SQB is a right triangle. So in the next step, implement the Pythagoras theorem on this green small right triangle SQB. According to the Pythagoras theorem, and this right triangle SQB, QS squared, that is the square of the hypotenuse, equals to QB squared plus VS squared. Okay, again, according to the Pythagoras theorem, on this green small right triangle, again QBS, QS squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. QS is 25, therefore QS squared is 25 squared, that is 625, and is equals to QB squared. QB is 8, therefore QB squared is 8 squared. Plus SB squared. SB is 35 minus 8, therefore SB squared is 55 minus 8 squared. So in total, if you found out that, according to the Pythagoras theorem, 625 equals to 8 squared plus 300 minus 8 squared. So 625 equals to 8 squared, and 35 minus 8 squared equals to 35 squared, that is 1225, plus 8 squared, minus 2 times 35 times 8, that is 178. So 625 equals to 8 squared plus 8 squared is 2 8 squared, and we have here 178 plus 1225. 625 equals to 2 8 squared minus 78 plus 1225. Here we subtract 625 from this equation. So in this side of the equation we left with nothing, that is to say 0, and on the other side of the equation we have 2 8 squared minus 78, and 1225 minus 625 is 600. So in total, if you want to know that 0 equals to 2 8 squared minus 78 plus 600. Here we divided this equation by 2, and finally found out that 0 over 2 is 0, 2 8 squared over 2 is 8 squared, 178 over 2 is 145a, and 600 over 2 is 300. So in total, if you found out that a squared minus 45a plus 300 equals to 0. So actually this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. You have a specific quadratic equation that is to say a squared minus 45a plus 300 equals to 0. The variable that you are looking for is a, so x equals to a. The coefficient a equals to 1, the coefficient b equals to 145, and the coefficient c equals to 300. So we have all the data that is needed in order to find out the variable that you are looking for in our specific quadratic equation, that is a. You just have to put the data inside this general formula form, x, and this way we find out the value of the values of a, because the value that we're looking for, our specific quadratic equation is a. So x equals to a, so we substitute x by a. And it equals to minus b. B is 145, therefore minus b is 145, that is plus 25, plus minus square root of b squared. B is 145, therefore b squared is 145 squared, that is 1225, minus 4 times a times c. A is 1, c is 300, so minus 4 times a times c is minus 4 times 1 times 300, that is minus 1200 over 2a. A is 1, so 2a, 2 times 1, that is 2. So total we found out that a equals to 35 plus minus square root of 1225 minus 1200 over 2. 1225 minus 1200 is 25, so inside the root we left only 25. So in total we found out that a equals to 35 plus minus square root of 25 over 2. The square root of 25 is 5, so in total we found out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So actually, the first solution for a is that a equals to 20. The second solution for a is that a equals to 35 times 5 over 2. 35 times 5 is 30, and 30 over 2 is 15. So the second solution for a is that a equals to 15, and the first solution for a is that a equals to 20. In the next step, we focus on this right triangle AQP. The triangle AQP is an associated triangle because side AQ equals to side AP. QP is the base of this associated triangle AQP. So from point A we do perpendicular to the base QP. Again, from point A we do perpendicular to the base QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in the base QP. This point is point Z. So now we can implement rule 21 in our drawing, and this associated triangle AQP. Okay, rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. ABC is an associated triangle because AB equals to AC. BC is of course the base of this associated triangle, triangle ABC. From point A we do perpendicular AO to the base BC. Again, from point A we do perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this rule 21, the perpendicular AO bisect the base BC. Again, the perpendicular AO to the base BC bisect the base BC. So BC is being bisected, therefore each half must be equal to BC over 2, of course. So the first half BO equals to the second half OC, and each half must be equal to BC over 2. So BO equals to OC equals to BC over 2. According to this rule 21. So we can implement rule 21 in our drawing. In our drawing, this is the green associated triangle AQP. And we have the perpendicular AZ, according to rule 21, the perpendicular AZ to the base QP bisect the base QP. So the first half is QZ, it must be equal to the second half QP, each half must be also equal to QP over 2. So QP equals to ZP equals to QP over 2. Again, QZ equals to ZP equals to QP over 2. According to rule 21, the perpendicular AZ to the base QP bisect the base QP. The first half QZ equals to the second half ZP, and each half must be equal to QP over 2. QP is 24, 24 over 2 is 12. So from this equation, we derive that QZ equals to ZP equals to 12. So ZP equals to 12, and QZ also equals to 12. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to all the dimensions. So in this green rectangle AQZ, this angle this angle equals to alpha, this angle equals to 90 degrees, therefore this first angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in this small green triangle QSB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha according to the symbol that says that the sum of the angles in any triangle is equal to 180 degrees. Those two green rectangles are similar to each other according to angle similar to. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the figures of this small rectangle SQB are corresponding equal to all the figures of this big rectangle AQZ, and therefore those two rectangles are similar to each other according to angle similar to. So if you found out the small rectangle QBS is similar, this is a sign of similar to the big rectangle AQZ according to angle similar to. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SQ of this small rectangle SQB or side SQ of this small rectangle SQB or side AQ of this big rectangle AQZ is equal to side QB of this small rectangle SQB or side QZ of this big rectangle AQZ. Then again, from the fact that those two rectangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SQ of the small rectangle SQB or side AQ of the big rectangle AQZ is equal to side QB of the small rectangle SQB or side QZ of the big rectangle AQZ. QS is 25, AQ is X, QB is A, and QZ is 12. So in total, if you found out that 25 over X equals to A over 12. Here we cross multiply this equation, if I found out that 25 times 12 is 300, 300 equals to 8 times X. Here we divided this equation by A, and I found out that X equals to 300 over A units in its length. So, we have two solutions that are possible for A. A could be equal to either 15 or to 20. Maybe we have two solutions for A. We don't know. In order to verify what is the real value of A, I copied this rectangle ABC, the second that is described inside it, the new drawing, and I asked the new drawing in order to find out what is the real value of A. So this is actually the rectangle ABC, the second that is described inside it, and the point from the original drawing. We only found out that AQ equals to X, QB equals to A. So here we define the point of tendency of the ABC with this second. This point is point M. We define the center of this second. This point is point O. We define the radius of this second as R. The next step, we join points O and M together by straight line. Point O is the center of the second. Point M is the point of the second itself. Therefore, OM is the radius of the second. Is equals to R according to our definition. The radius of M is equals to R. The radius of M is drawn to point M. That is the point of tendency of tangent BC with this second. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Point Q is the point of tendency of tangent AB with this second. We join points O and Q together by straight line. OQ is the radius of the second that is equals to R. And according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees in size. The small quadrilateral OQBM, we have 1, 2, 3 rectangles, and therefore this fourth angle must be equal to 90 degrees in size according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, in the small quadrilateral OQBM, we have 4 rectangles, and therefore it is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle OQBM, side OM must be equal to the opposite side QB, but OM is out, therefore the opposite side QB must be also equal to R units in itself. So in total, if you found out that QB equals to A equals to R. The next step we do the construction, that is to say we extend the radius OM by side line until it touches the circle at this point. We define the touching point of the extended radius OM with this circle. This point is point Z. OM is the radius of the circle that is absolutely a straight line. When you extend a straight line by straight line, the result MZ must be also a straight line. So MZ is a straight line. If you focus on the right side of the straight line ZM at point O, here the sum of the areas must be equal to 180 degrees according to all three. All three says that the sum of the areas from one side of the straight line is equal to 180 degrees. So which areas we have the right side of the straight line ZM at point O, we have this angle that is the right angle, plus this missing angle, in total the sum of those two areas must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we did the construction, that is to say from side AB of the rectangle ABC we draw tangent to the circle at point Z. Again from AB we draw tangent to the circle at point Z. We find the touching point of the tangent with this side AB, this point is point T. Repeat again, the TZ is the tangent to point Z according to our construction. Again TZ is the tangent to this circle at point Z according to our construction. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle, that is equals to R. The radius OZ is equals to R, the radius OZ is drawn to point Z, that is the point of tendency of tangent Z with this circle. And whenever the radius is drawn to the point of tendency, then tangent OZ will be perpendicular to, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees, this angle equals to 90 degrees according to all 1. So in total, in the upper quadrangle TZ or Q, we have 1, 2, 3 degrees. This angle equals to 90 degrees according to all 3. So we have 1, 2, 3 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle TZ or Q we have 4 rectangles and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle TZ or Q, side ZO must be equal to the opposite side TQ. But ZO is R, therefore the opposite side TQ must be also equal to R unit in its length. So we only found out that QB equals to R and QB also equals to A. And again QB equals to R and QB also equals to A. Likewise, AQ equals to X, and AQ also equals to AT plus TQ. So AQ in total equals to AT plus TQ. TQ is also, in total, AQ equals to AT plus R. Repeat again, QB, AQ equals to X, and AQ also equals to AT plus R. Again, AQ equals to X, and AQ also equals to AT plus R. AT is the length of this line segment. AT is the length, it is absolutely a positive number. Therefore, AT plus R must be greater than R because AT is a positive number. So AT plus R is greater than R. From this log inequality, we know that A is smaller than X. Again, A is smaller than X. A is smaller than X, so X is greater than A. Okay? X is greater than A. X is greater than A. So just like the formula that X is greater than A. So we have two solutions that are possible for A. A could be equal to either 20 or to 15. We already found out that X equals to 300 over A. So we find that X equals to 300 over A. So according to this equation, if A equals to 15, then X must be equal to 300 over 15, that is 20. So if A equals to 15, then X must be equal to 20. Likewise, according to the same equation, this equation, if A equals to 20, then X must be equal to 300 over 20, that is 15. So in conclusion, found out that if A equals to 20, then X must be equal to 15. And if A equals to 15, then X must be equal to 20. So X equals to 15, 15 is definitely less than 20, and 20 equals to A. So can I do that 20 equals to A? From this inequality, we'll derive that x is less than 20. X is less than 20. It contradicts our previous findings that x must be greater than a. If x must be greater than a, x cannot be less than a. So due to this contradiction, we cancel this solution for a can never be equal to 20. And we'll take into account only the second solution for a. If a equals to 15, then x must be equal to 20. So x equals to 20. 20 is definitely greater than 15. It equals to a. 15 equals to a. From this inequality, we derive that x is greater than a. Exactly according to our previous findings that x is greater than a. So the solution to the question is that line 78p equals to x is equal to 20 units in its length. Repeat again. Found out that this is line 78p. This equals to x is equal to 20 units in its length. Okay, thank you very much.